All right, now we are going to go into section 12.2. Section 12.2 is the test for independence and homogeneity of proportions. Um, so you'll notice that this is kind of similar to section 12.1, just taken to the next level. There's a lot of similarities, but it's a little more complicated. Um, kind of the steps you do for the hypothesis test are very similar, but it's going to be more complex because instead of just having one column of numbers like in section 12.1 where we just have the frequencies of the numbers, we're going to actually have like a matrix, like a kind of like Excel, like you have like a 3x4 rectangle with numbers in them. You'll see what I'm talking about in a minute. And so you're going to be dealing with a lot more numbers, but it's the same calculation of like chi-squared, where we do observed squared divided by expected, and add all the different numbers up with that equation, and then subtract n, or use that equation that's in the book. There's just a lot more numbers to deal with. But the convenient part of this is that we can use our calculator to do a lot of the work for you, because there is actually a test for the test for independence in your calculator that will allow you to do this very fast. Unfortunately, some calculators, depending on which one you have, I know that TI-83 does not have it. TI-84, it depends on which version of the TI-84 you have. One may have it, one may not. T89 has it, the TI-89. Inspire might have it. I'm not really sure. I haven't played with the Inspire too much. But anyways, for section 12.1, you can actually program something to make the test work for you and calculate the test statistic instead of doing it by hand. But it's not too bad doing it by hand. Usually only add up a few numbers we're using that equation. So anyways, I will provide you a link with how to program your calculator, instructions through the website that explains how to calculate or how to program your calculator to be able to calculate the test statistic for the 12.1 goodness of fit test. But it's already in your calculator. It should be in 83 and 84 and all the calculators for the test for independence. So let's go ahead and go over that. So the test for independence is dealing with a very similar sort of thing that we were dealing with before, but in section 12.1. But in this case, we're comparing two different variables where you can have where each of the variables are categorical, and we're going to test how they interact with each other, and test if they're independent of each other. And there's a property or an equation that you may remember from Math 243 of independence, where two variables are independent if the probability of variable A and B is equal to the probability of A times the probability of B. We would say A and B are independent if this equation is true. Okay, so we can actually use this equation to help us out to determine why we're using the equations we're using in section 12.2. So I will go ahead and help you work out a problem with this equation to aid us to determine the actual expected of a certain category. So let's go ahead and find a problem. Let's go ahead and do let's go ahead don't want to deal with a lot of numbers. Hey, let's deal with a controversial issue: pro-life or pro-choice. There's only 4 numbers, that's why I actually chose it. But anyways, this is problem 12 in section 12.2, or 5.2 if you have the custom book. So number 12, it says pro-life or pro-choice. Okay, so we're a recent Gallup poll. We're actually only going to do part A because I really don't care about determining. We'll go ahead and do part B too. Well, we'll see. Anyways, we're gonna focus on part A because that's where all the calculations are involved, and part B is pretty straightforward. After we do it, we'll see that it's pretty straightforward. So, a recent Gallup organization poll asked male and female Americans whether they were pro-life or pro-choice when it comes to abortion issues. The results of the survey are as follows. So, this is based off of a sample. We have, so it's given here already. So, we have 2 variables, as you can see. There's gender, and so we have men and women. So it's categorical. The first variable is gender, and we can see it's categorical. They could either be men or women. And then we have another categorical, pro-life or pro-choice. So either you're pro-life, so this is obviously categorical, or pro-choice. Okay. And based off the sample, we at least found that we have 196, 199, 239, and 249. This is based off of the sample. This is not the expected amount that is claimed. So from this example, at least reading the problem, test whether an individual's opinion regarding abortion is independent of gender. So the independence test is based off of this equation right here. Okay, so I'm going to let you just kind of read up on the steps of the null and alternative hypothesis, or at least I'll do that on the next page. Actually, I'm going to just show you where we're going to get the expected. So these are the observed. These are O sub i's, like from section 12.1. These are the observed because this is from the sample. So I'll show you where the expected comes from. It's based off the totals, kind of like from section 12.1, but the totals is based off of each row and column, the totals from each row and column. And we'll actually get a total of everything in a second. So 196 plus 239, don't want to do it in my head because I'm lazy right now. 196 plus 239 is 435. And then 199 over 2, I can see that that's 448. And then we have 196 plus 199. That is 395. And then we have 249. I don't want to do this. 239 plus 249. Don't judge me. Here we go. 488. We have 488 people. Okay. And so what we see here is, okay, so we have a total. We can just add up either this row or this column and get the total. Obviously, 395 plus 488 is 883. You'll get the same number if you add this row here. So there's your total of all the values. Okay, so we're going to use this information here to help us figure out what the expected amount would be if they were independent using this equation. Okay, and okay, so we're going to actually figure out what E sub I is. So we're going to have the same thing: gender, men, women, and then pro-life, and then pro-choice. Right, and there we go. We're going to fill in this chart based off of these numbers right here in this equation. So how are we going to do that? So what would, if they are independent, we're going to assume that they're independent to determine the expected values if they were independent. If they were independent, they would make this equation would be true. So the probability of A, so the probability, for example, of pro-life and times the probability of being a male should equal this cell right here, pro-life and male. But we should be able to use this equation of taking the product of a pro-life, which is 438, or 435. The probability that you have a pro-life person is 435 over 883. Okay, so 443, yeah, 435, sorry. So using the equation, probability of, I'll call it pro-life, times the and male is equal to, so that would be this cell right here, because that's pro-life and male, this cell. It would be equal to the probability of a pro-life. The probability of a pro-life is 435 over 883 times the probability of a male, right? Probability of a male, which is 395 over 883. And then, so that will give us the probability of a pro-life and a male. But we don't want to just find the probability. We want to find the count. And the count is based off of multiplying by the sample size. So we'll want to multiply that by n on both sides, which would be 883, which is equivalent to so notice that 883 cancels out with 883. And so all we have to really do is multiply 435 by 395 and divide by 883. Notice by that equation right there. So we have 435 times 395 divide 883. So we would expect 194.59. It's good to be able to round to a couple decimals, even though it doesn't make sense to have that many people. We don't want rounding error, so let's round to 2 decimals, let's just say. So that would be 194.59. That is the expected count of pro-life and male people, which would be the cell right here. Similarly, we can calculate this cell right here. I'll just put a star right there, by multiplying this number, because it's a pro-life woman, so we'd multiply 435 by 488, because that's the woman column, or a row, and total, and then divide by 883. So let's do that. 435 multiplied 488 divide 883. Because as you can see, one of the 883s cancels out. So all we're doing is the count of whatever the total of one row, and then multiplied by the count of the total of our column and then row, and then divided by the total. Okay. So I got oops. Let's insert 240.4 1. And then similarly, we can do, for this, it would be pro-choice male. So pro-choice total is 448, male 395. So 448 times 395 divide 883, 200.41. And lastly, we would do this cell, which would be 448 times 488. 448 times 488 divide 883. 247.59. And so, in order to be independent, it has to follow this equation, which is the independence equation. And what we notice is, based off of that, we would expect, if they're independent, to have these numbers. Now, again, similar to 12.1, you can kind of just observe and see how accurate it is. And we notice that this number is really close to this number. This number is really close to that number. This number is really close to this number. And this number is really close to this number. I expect to see a fail to reject H naught. Because H naught, based off, we haven't done H naught yet, but you know H naught involves equality. That's just saying that it is independent. That is what the claim will be. That gender and pro-life versus pro-choice, those two variables will be independent of each other. And I'm pretty sure that we're going to fail to reject that H naught in that case, because these numbers are really matching up. But we still have to go through with it. So we've done a lot of the steps of the hypothesis test. And just as I mentioned before, a lot of these steps are similar to 12.1. And that being, so we've done a lot of the work. You can refer back to this, and I'll show you this from time to time when needed. So step 1. So we don't have any preliminary checks yet, because remember from 12.1, they don't come until step 3. So H naught in this case, as mentioned, is that the row variable and the column variable are independent of each other. So based off of this, we would say that pro-life or gender, and I'll just say pro-life versus pro-choice variables are independent of each other. That would be the null hypothesis, that the thing is equivalent. They are true. That this equation is going to hold up based off of our sample. That's what we're saying. Based off of our sample, this is going to hold up. It's going to be independent. And then we have the alternative hypothesis, which is just the opposite, similar to 12.1. Gender and pro-life versus pro-choice variables. And the opposite of independent is dependent. There's step 1. Step 2, like usual, I don't even know what we're doing here. Let's see here. Step 2, we're dealing with alpha equal blah, 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 0.1, stated in part A. Alpha equals 0.1. Okay, there we go. We have alpha. Let's move on to step 3. We've done a lot of step 3 already, but we have, remember, the preliminary checks. Actually, part A is all this. All this work we just did here, this is actually 3A. I wanted to do that first to just kind of show you what was going on. And you can see that it's kind of similar to section 12.1. So part A is done. We're done with that. Part B is to verify the requirements are held. And if you remember, it's identical. All expected frequencies are greater than or equal to 1. The expected frequencies are E sub I, remember. And in this case, E sub I is assuming that they're independent. What values would you get? Are all of them greater than or equal to 1? As we can see, they're huge. So check. 2. Are more than 20% less than or equal to 5? And as we can see, they're all huge. They're all beyond 5. So, bam, we're done. All right, so preliminary checks are held. And so now we can move on to step 3, which is compute the test statistic. Now, conveniently, as mentioned, we can use our calculator. And I'm going to go ahead and do that because I really don't want to add these up. It's not too bad. All we would do is we would use the equation of chi squared naught equals the summation of, and remember I like this equation better. You can use the one in the book, minus n. And you will actually get the same thing with your calculator. And I'm not going to use that. And obviously you would take like 196 squared, divide this, plus 199 squared, divide this, and so forth. And then subtract n, and n in this case is 883. Remember, 883, that's your n. We can do that, or actually, just to show you that we get the same answer, I'm going to go ahead and do it. We're not that far in time in the video, so it's not that long. Okay, so 196 squared over 194.59 plus 199 squared divided by 200. And obviously, it doesn't matter in what order you do it. You just have to make sure that if you do the top left, you have to divide by the top left and keep them all straight like that. But all right, I'm going to continue down here. We have 239. And obviously, this one isn't too bad, but you can imagine if you had like a 3x5 matrix, there's 15 different things that you'll be adding together. That's going to suck. You might as well use your calculator. But we only have 4 things, so I'm going to go ahead and do it. Plus squared plus 249 squared over 247.59 minus, as mentioned, 883. And I'm going to plug this into the calculator really quickly. So we have 196 squared divide 194.59 plus 199 squared divide 200.41 plus 239 squared divide 240.41 plus 249 squared divide 247.59 minus 883. Holy cow. I ended up getting, wow, 0.36. Really? All right, let's see if this is true. 43644, I'll just say. All right, so how you do this on your calculator, just to let you know, we can flip back to that, but you'll be using the, oh, you can see that pretty well. I don't need to write it down. Okay, so you are going to be using the stat tests, the chi-squared test. Okay, so the chi-squared test only works in section 12.2. It does not work in the section 12.1 information. So, anyways, let's go ahead and continue. First, we have to make a matrix. If you haven't used this before, you want to go to your matrix button to depending on which calculator you have, it may be second x to the negative 1. But anyways, it should look like this, and then you want to edit the first, and notice that it's a 2 by 2 matrix because we have 2 possible values for each category. And so you want to do, I'm going to go ahead and do the observed first. Yeah, let's just do observed first. 196, 199, 239, and 249. Okay, and we need to go to second matrix and 2, 2. We need to make another matrix for expected. So we have 194.59, 200.41, 240.41. What just happened? Apparently something didn't enter. 194.59, 200.41, and 240.41, 247.59. All right, so we made our 2 matrices. We have A and B. Observed is A, and expected is B. So we'll go back to stat tests and chi-squared test. Notice observed is A, but if you need to, let's say you don't have A and B in there, you would want to, let's just say clear it. If you wanted to put matrix A in there, you would just go over to matrix, second matrix, and hit A. Hit enter A, and it'll put A in there. Don't move over to a different. You're on the matrix. But anyways, there you go. And we're going to go ahead and calculate. Oh, look at that. Good. So notice that our chi-squared value is 0.0363, which is really close to what we just got here, probably due to rounding error. Okay. So notice that the degrees of freedom is equal to 1. That's interesting. Wonder how they got that. So how they got that, and notice it gives you your p-value. Your p-value is also given to you if you're asked for that in a problem. You may want to find the p-value. There you go. There's your p-value. Degrees of freedom of 1. How do they get that? It's based off of the amount of rows and the amount of columns. It's r minus 1 times c minus 1. Rows minus 1 times columns minus 1. 2 rows, 2 columns, so it's really just 2 minus 1 times 2 minus 1. So that's 1 times 1, which is 1. I'll write it down in a second since we're not quite there yet to the critical value. But as you can see, we used our chi-squared test, and we can use that so we don't have to do all this stuff right here. But we still have to do all this stuff here, this preliminary work. So there's enough preliminary work in itself. Okay, so but to find our test statistic and our p-value and our degrees of freedom and whatever, we can use our chi-squared test on our calculator. Okay, so now we're on step 4. Step 4 is to find the test statistic or critical value. So step 4. Step 4 is to find the critical value, and the critical value is chi-squared alpha. It's a right-tailed test again, similar to 12.1, and what is our alpha? What is our alpha? Let's go back here. Our alpha is 0.1. Okay, so 0.1. Okay, and with df equals rows minus 1, columns minus 1. Since there's, how many rows do we have? We have 2 rows, so it's 2 minus 1. How many columns do we have? There's 2 possibilities. You're pro-life or pro-choice, so it's 2 minus 1. So it's 2 so as you can see, it's just 1 degrees of freedom. And that's how you calculate it. Kind of weird, but not too bad. All right, so our test statistic. We would go back to the chi-squared table, and we would look under point 1, and we would find degrees of freedom 1, 2.706. 2.706. Their test statistic. Excuse me. So as you can see, comparing, we have the boundary of 2.706. The far left is 0, as you know, for a chi-squared distribution. And as you can see, or you remember, we had a value of a chi-squared of 0.036 for our test statistic. 0.036 is way over here. So obviously this is they fail to reject H0 because our test statistic is over here. Okay. And the rejection would be over this way. So we failed to reject H0. All right. So our conclusion would be, well, step 5. So go to the flow chart as always mentioned. You want to, okay, first figure out, do we have the condition of equality? And in this case, equality is what H0 is mentioned as, and it's being independent. Does the claim say that it is independent? And as you can see, in part A, it says, test whether an individual's opinion regarding abortion is independent of gender. So, yes. The answer is yes. It does have the condition of equality, which is stating it is independent in the claim. Did we reject? No. So we're in option 2 of our flow chart, of our wording. Okay? So I don't have the flow chart with me, but you'll say the words that are on the flow chart, and then you would just copy and paste in the claim. An individual's opinion regarding abortion is independent of gender, which is pretty much saying regardless of if you're male or female, it doesn't affect the proportion of you'd expect the same proportion of male and females to be pro-life or pro-choice. Okay. Oh, and at alpha, as mentioned before, you want to include this 0.1 level of significance. There's an example of a test for independence. And the reason that they mention the other part, the homogeneity of proportions, is that it's the same exact process. The only difference, it's literally the same exact process in regards to how you calculate it. The only difference is that you're dealing with, let's go back to an example. So I'll just show you where. let's just find it. Oh yeah, and part B in regards to part B of that problem, construct a conditional distribution. They actually show you an example in the book. I really don't want to do this right now. But yeah, I would just say that it's a good exercise just to look in the book. There's several examples before the exercises. Actually, it might only be one. Yeah, there's just one example. Example 3, figure 13, where they actually show you a conditional probability distribution. Bar graph. So it's pretty straightforward. Anyways, gosh, where am I looking? Okay, so homogeneity of proportions. The only difference is how you state the null and alternative hypothesis. Instead of talking about independence, it's I'm not going to go over an example because it's almost identical. It's just the wording of the wording of the null and alternative hypothesis is different. So proportions, what it's actually doing is you're comparing more than one proportion. So that's the difference between the difference of proportions from chapter 11 and the homogeneity of proportions, is that they're testing more than more than two proportions in chapter 12. It can be 3, 4, 5, up to however many. And so this is just an example where they're looking at proportions. And the idea is that you do the same exact process where you add up the totals of each column and you do the independence equation. It's actually an independence. Testing more than two proportions is doing an independence test. So anyways, you just state it pretty much how it's stated here in example 4. I would suggest looking at example 4 to kind of understand it. But it's the same exact process in building a table similar to this, where you had to add up the totals and then multiply the observed of one row, the column, divide by the total, and you get each of the expected, assuming that the proportions are equal when you're dealing with a proportion problem. So anyways, you can look at example 4 to see how this has worked out if you're a little confused, but it's pretty much identical, as you can see right here. Row, column, divided by the total. You get an expected value to get what you need. And you can still use, as you can see, you can still use the chi-squared test for the proportions because it's identical to independence. And you get your conclusion the same exact way. And just make sure you address your claim on the conclusion, similar to what we've been talking about. Anyways, if you need an example of that, go ahead and let me know. But it's pretty straightforward in comparison. Well, it's identical to 12, the example I just did in this 12.2 video. Anyways, good luck with what you with your work, and I'm going to update the cheat sheet for stuff you can do in your calculator with what we've just done here and all of Chapter 11 stuff. I haven't updated Chapter 11 stuff yet. So you'll see an updated cheat sheet for tricks for your TI-83 or graphing calculator. Okay? Good luck. Bye.